So welcome everyone to our global non-commutative geometry seminar today. So our speaker is Marc Rieffel from UC Berkeley. So Marc is going to tell us about Dirac operators for matrix algebras converge to coadjoint objects. So Marc, please.
Thank you. I want to thank the organizers very much for giving me a chance to talk. In fact, they gave me two chances to talk. Some of you may have been at my first attempt to talk that was quite a failure. I was not able to appear. And what happened is my computer system and everything was working fine a few minutes before I was supposed to do the talk. But when I tried to connect to the link for the talk, I kept getting error messages about can't find the server and things like that, and tried various things and couldn't get anywhere, and finally had to give up. And I was able to contact Chang about that. And I found out a little bit later that what happened was that my internet connection had failed, and not only had it failed for me, but for the whole 300-person senior community that I live in, and for some of the local shops and so on. And it took Comcast 3 or 4 hours to restore the service. So that was why I didn't make my appearance. We will hope that that doesn't happen again. Anyway, I'm very pleased to be here to talk to all of you about this topic that I've been pursuing actually for a number of years, the business about matrix algebras, converge to the sphere. Some of you have heard me talk about earlier aspects of that, but this is the first time I've gotten well, finally results about Dirac operators and so on, and that's what I want to tell you about today. And so let me start the outline of the talk. I'll sketch a somewhat crude Dirac type operator for any ergodic action of a compact Lie group on a unital C-star algebra. That will be the sort of unifying framework. And I'll indicate the definition of a C-star metric space on a C-star algebra, and excuse me, a C-star metric on a C-star algebra, and how one obtains C-star metrics from Dirac operators. And then I'll show how the construction works specifically for the matrix algebras associated with irreducible representations of a compact Lie group. And I'll discuss how the construction relates to the homogeneous spaces, especially the ones that are coadjoint orbits. And then finally, I'll be able to say a little bit about what it means for the matrix algebras to converge to the coadjoint orbits. And this is all a quite long story, and I simply will not have time for many of details, and even some of the statements I make may not be exactly right because there isn't time to give you the full story about that. So anyway, everything will be based on a connected compact Lie group, very soon assumed to be a semi-simple Lie group, and that group will be fixed for the talk. So just think of SU2 or SUN or orthogonal groups, so on as the underlying group, but I won't change the group during the whole talk. And coadjoint orbits can be viewed as homogeneous spaces, so G over K. I'll indicate how that works, and we have an action of the group on the homogeneous space by translation. And then on the other hand, if we have any irreducible unitary representation of the group, we let this curly B be the space of all of the operators on the finite dimensional Hilbert space for this representation. And that's, of course, isomorphic to a full matrix algebra. And these will be the matrix algebras that are mentioned in the title. And we define an action alpha of G on curly B just by conjugating by the representation. And what we notice is that both of these types of actions, the ones on the homogeneous spaces and the ones on these matrix algebras, are ergodic, which is just a fancy word for saying that the only elements in the algebras that are left fixed by the actions are scalar multiples of the identity elements. So the sort of crude setting that we use at first will apply to both of these cases is that we have a C star algebra A and an action alpha of G on that C star algebra, and this action is ergodic. So we will define a Dirac type operator in this general setting. It'll have some deficiencies that I will mention, but nevertheless, it's crucial for the proof of our main theorem. And to start out on how that goes, we let A infinity denote the dense subalgebra of infinitely differentiable elements for alpha. It's carried into itself by alpha. And we let this frac G be the Lie algebra of G, and we have a corresponding representation of the Lie algebra as operators on the C infinity elements. But it's actually by star derivations. And that comes just from the action of the group. And then we let this frac G prime denote the vector space dual of G. And G has its adjoint action on the Lie algebra, and just the dual of that is the co-action that we have on the dual of the Lie algebra. And each element of A infinity determines a linear function, denoted dA, from the Lie algebra into the C infinity elements, and it's defined just, well, you see the formula there. This formula here that I won't try to say, and you can view these as differential forms, and as such they can be viewed as elements of the tensor product of A infinity with G prime. I mean, this might be a little bit confusing at first because A infinity is over the complex numbers and G prime is over the real numbers, but this is just tensor product over the real numbers. And we let omega sub 0 be the A infinity bimodule of all linear functions from G into A infinity, and it can be identified exactly with this A infinity tensored with the dual of the Lie algebra. And we view this as the actually cross-section bimodule of the smooth complexified cotangent bundle for A infinity. I mean, this is heuristic since we don't have an actual bundle in the classical sense here. And then D sending A into dA is a derivation from A infinity into this bimodule, and it can be considered the total derivative of A. So then we view the dual of the Lie algebra as a typical cotangent fiber. Again, all this is heuristic, and we choose an inner product on it, and we require that this inner product be invariant under the coadjoint action, and certainly one choice is the negative of the killing inner product. for those of you who know what that is. And then the action, the coadjoint action is by orthogonal operators. Okay. Then using that inner product, we define an A infinity valued inner product on our cotangent bundle just by the formula that you see displayed here, very natural and simple definition. And this serves as our Riemannian metric. And then we next need the Clifford algebra bundle for our Riemannian metric. And for that, we use the complex Clifford algebra over the dual of the Lie algebra, where we're using the inner product that we chose on the dual of the Lie algebra. So the Clifford algebra, it's the unital algebra over the complex numbers that's generated by the dual of the Lie algebra as a real linear subspace. And I write here the defining, this pretty standard defining relation. And there's always a question as to whether you put in a plus or a minus sign here, and I choose to put in the minus sign. And since the action, the coadjoint action on the dual of the Lie algebra is by orthogonal operators, it extends to an action of the Clifford algebra by star automorphisms. And we'll denote that action again by CAD. And there's a corresponding action of the Lie algebra of the group by star derivations of the Clifford algebra. And then we can take the tensor product of A infinity with this Clifford algebra, and that's the Clifford algebra bundle, really meaning the analog of the cross sections of the Clifford algebra bundle for our given choice of a Riemannian metric. And depending on whether the dimension of the Lie algebra is even or odd, this Clifford algebra will have one or two irreducible representations up to equivalent, and we make a choice of one of these two representations and denote it by this script S, and use K as the denoting the representation, the K being for Clifford, except that there are too many C's around in the notation here, so we use K and instead, and this representation is often called a spinor representation. And then our spinor bundle, just an analogy with what we did before, is A infinity tensored with this spinor bundle, and that's we can view it as a module over the Clifford algebra bundle, with K's denoting the corresponding multiplication or action. So then our Dirac type operator, I mean, it's all quite straightforward in this simple setting where basically all of our modules are free modules over A infinity. It's just the composition of the first step here, where we're using just the mapping from A infinity into the cotangent bundle, and then we, as our second mapping, this is just the embedding of the dual of the Lie algebra into its Clifford algebra, and then the third map here is simply applying the representation of the Clifford algebra on the Clifford bundle. And this all can be expressed, as I say, in a somewhat cryptic form by this very short formula that I have here. and to obtain a somewhat more familiar form for this operator, we can choose a basis for the Lie algebra and then the dual basis for the dual of the Lie algebra, and then one gets the formula at the bottom here. It looks pretty similar to the formulas for more complicated Dirac operators in the geometric setting. So all of this can be made equivariant for the action of G. The one small stumbling place is for getting a suitable action on the spinor bundle, and for that you need G simply connected. Here I'm really assuming that G is semi-simple compact. So the simply connected covering group is again going to be compact. And then we can, if we take an element A, we can let M sub A denote the operator of on our spinor bundle corresponding to the left regular representation of A infinity on itself. And then we look at the commutator with this Dirac type operator. And here on the right, I've simplified the notation, and because of too many subscripts, I've written that instead of this term here, and I'll do that somewhat consistently as we go along. Too many levels of subscripts, and then there is it's a basic theorem going back to Hogue, Krohn, and Landstadt and Sturmer, that there's a unique alpha invariant trace on our unital C-star algebra for which the action is ergodic, and we use this trace to define, and let's see, I guess I probably should, for uniqueness, I should have said tracial state, but that's not so important. We use this to define an ordinary inner product on our spinor bundle just by the simple formula given here. And for this formula, we see easily that this commutator gives a bounded operator on the spinor bundle, and so on its Hilbert space completion, and that, so you can, again, this is the standard type of thing that happens if you have a nice Dirac operator. And using this, we can define a semi-norm, much as Alain Connes did for his Dirac operators, by just taking the semi-norm on an element A of our smooth algebra just to be the operator norm of this commutant. And then in my very first paper on all this kind of thing, I did this construction very briefly, and I didn't at that time have a definition of a C-star metric. I'll give that in a moment. But I did give a proof in that paper of what turns out to be the most well, the condition for a C-star metric, which is most difficult to verify for various examples. So for any unital C-star algebra, by a C-star metric, I mean a semi-norm that's defined on a unital dense star subalgebra. It's not necessarily continuous with respect to the norm of the algebra, but it has the following properties. Well, just the simple properties that on any element, it's zero only if and only if that element is a scalar multiple of the identity element. that's related to this ergodicity that I've been talking about, and you want it to represent the star condition, and it's nice to have it be lower semi-continuous. If it's not lower semi-continuous, then you can always find a corresponding lower semi-continuous one. And very important is this Leibniz inequality. And then, as I say, there's this crucial property that I will now explain, the one that I did give a proof for in that first paper. Namely, we let script S of A be the state space of A. And then again, much as Alain did for the semi-norm from his spectral triple, we use that semi-norm to define a metric on the state space by this formula that I have here. And that's all looks very general, and it is, and without further hypotheses, this metric can take the value plus infinity, so it's an extended metric. But in fact, for our, well, the properties that we need in order to view L as being a C-star metric is that the topology on the state space just determined by this metric, it coincides with the weak star topology, and that certainly in particular means that the metric always takes finite values, but it's considerably stronger than that. So by a compact C-star metric space, I just mean a pair consisting of unital C-star algebra equipped with a specific C-star metric as defined above. And so for an ergodic action of G on A, as discussed above, when we equip our algebra with its ergodic action by the semi-norm obtained from this sort of crude Dirac operator that I defined earlier, that is going to be a C-star metric space, satisfying all those conditions. The main deficiency of this approach is that the usual definition of the cotangent bundle requires that it be generated as a bimodule by the range of the derivation D. And this fails for many ergodic actions of the type that I've mentioned above. And so this first definition of the cotangent is often too big to be the appropriate cotangent bundle. But let's consider what happens for the case of an irreducible representation and the corresponding matrix algebra and so on. A theorem, and I have a little published paper in which I give the proof of this, is that if the representation of the group, it happens to be a faithful representation, which will of course happen if the group is actually a simple Lie group, then the range of D does in fact generate all of this bimodule that I had defined earlier, and so that really is the appropriate cotangent bundle. And if the unitary representation isn't faithful, well, you just look at the complementary ideal in the Lie algebra, complementary to the kernel of the representation, and then basically the same thing happens, namely that the range of D generates a tensor prime tensored with the the dual of this piece on which the representation is faithful. So in this situation, we don't always get the cotangent bundle as I described before, but the modification needed if to get it always is very minor. Okay. Let's see what happened here. Yeah, I think yeah. Okay. That's so yeah. For four matrix algebras, our Clifford bundle, we take we make the small modification as needed, and similarly for the using the Clifford algebra and so on, and just always using this smaller algebra, and then the Dirac operator du is defined above. These are the Dirac operators that I use for the matrix algebras, okay. And they determine corresponding C-star metrics in exactly the way I outlined above. So for the Dirac operators that been alluded to in the title of this talk, the Dirac operators on the matrix algebras are obtained in this pretty simple way. However, important for our proofs, I should say, is that with the notation as above, the semi-norm that you get in this way agrees with the semi-norm that you get from the crude Dirac operator that I defined earlier. That crude Dirac operator does in a certain sense see that that a representation may not be faithful and so on.
Sorry, I cannot read. Oh, okay.
Yes.
Now it's fine.
Yes. Thus, for metric purposes, we can continue to use the original semi-norm, and that's, as I say, that's helpful for the proofs. And then, on the other hand, the construction of Dirac operators for homogeneous spaces, G over K, that's much more complicated, and it gets to these questions about whether the homogeneous spaces are spin or spin C, and gets into connections and questions of whether the torsion is zero and all of that. But let's see what we can go a certain distance, namely just for general for K, just a general closed subgroup of G. You can let this frac K denote its the algebra, and then you look at you let this M prime in the dual of the Lie algebra of G be all of the linear functionals that are zero on the Lie algebra of K, and the restriction of the coadjoint representation to K, that will carry M prime into itself. And it's well known that the complexified cotangent bundle for G over K can be identified with, and here I'm leaving out the fact that I'm saying the cross section, the space of cross sections for that situation gives you the following projective submodule of our crude cotangent bundle, namely that it's all of the smooth functions from G into the complexification of M prime that satisfy this formula. And I didn't write it down, but those of you who are familiar with induced representations will recognize as simply the formula that you use for inducing a representation of K in this case, the coadjoint representation, reducing that up to G. This would be the space, at least before you complete it to get a Hilbert space. And so this is what this is the classical object, and that's certainly what we need to use in defining our Dirac operators for the cotangent. Well, for the coadjoint orbits, which are these quotient spaces. And the Clifford bundle is defined in an entirely similar way, and it's again it can be viewed as an induced representation, and the translation action of alpha of G on these spaces provides a connection on these bundles. I won't go into the details, and then so you get a Clifford algebra. Yeah, I should have put here Clifford algebra bundle, and you can try to define a spinor bundle in this way, but there you stumble into the problems about whether you have spin or spin C, or and so on, in order to have an appropriate spinor bundle. So those details I don't go into, but what happens for coadjoint orbits, and again, this is you have to really investigate somewhat deeply. They always admit an alpha invariant complex structure, and from this one sees that they are always spin C, even if they're not always spin. And so because of that, and again, I'm skipping lots of details, you can construct indeed the corresponding spinor bundle and use the connection from alpha to define, maybe I should, well, I maybe should have said a Dirac type operator. And the connection you get just from alpha is usually called the canonical connection, and I'll denote it by, denote the Dirac operator for it by this D decorated with a small c for canonical. And the problem is that the canonical connection is torsion free only when the coadjoint orbit is in fact a symmetric space, such as the sphere. So there are certainly plenty of these coadjoint orbits that are symmetric spaces and are of interest, but not all coadjoint orbits are symmetric spaces, and the usual Dirac operator is defined in terms of the corresponding torsion-free connection, the Levi-Civita connection, that's compatible with the Riemannian metric that we have. Okay, so our approach. And I don't know how in the setting of general ergodic actions on unital C-star algebras, I don't know how to define torsion free and things like that. So, and our approach really leads to the Levi-Civita connection only if the orbits are symmetric spaces. Well, and even for our general approach, for action just on any ergodic action on an algebra, it's not clear to me to what extent the submodule generated by D is going to be projective. I mean, there are a lot of questions there that are not clear to me. But anyway, for for all of our co-adjoint orbits, we have these Dirac operators. They have their associated semi-norms. So in particular, the one for the canonical connection and the one for the Levi-Civita connection. But what happens is that the semi-norms from all these Dirac operators all agree. Okay, so purely for metric purposes, we can continue to work with our Dirac operator, Dirac type operator, in spite of its deficiencies, and that simplifies our proofs substantially. But now we have to look more in more detail, I mean, at co-adjoint orbits and how they're related to the picture. So for that, we have to dive into the more detailed structure theory of. So we have to choose. I have no time, of course, to explain all of this, but what all this means. But a Cartan subalgebra and positive roots, and for each root you have corresponding standard operators that you can put a star structure on the complexified root space and so on, so that you can take adjoints of these elements. And then what happens is if we consider an irreducible unitary representation of G, then up to a phase there's a unique highest weight vector, unit vector, that I'll denote by xi sub diamond to really emphasize it. And it's characterized by being a common eigenvector for the Cartan subalgebra, but having the further property that for every positive root, the E sub alpha carries that root to 0. That's the condition that says it's highest weight vector. And for such a vector, we can define a linear functional x on our Lie algebra, and by the formula that I've given here. And so that's on the whole Lie algebra, but its restriction to the Cartan subalgebra is the what's called the highest weight of the representation. I mean, here I'm being, well, I use slightly different conventions for it's convenient, so that our weights are actually on this real Cartan subalgebra and not on I times it, as this is often done. And at the cost of sprinkling some square roots of -1 in a few places. So anyway, for that choice of linear functional, it's 0 on the rest of the space, and so now we've chosen our fixed representation, but now I want a sequence of matrix algebras that are going to converge to the coadjoint orbit. And to do that, for each positive integer, we let H super m and U super m be the irreducible representation of G, whose highest weight is m times our original representation. And all of these m mu's will have the same coadjoint stability subgroup, and they're all in the dual of the Lie algebra. And we will denote that stability subgroup by K, and that common coadjoint orbit we will view as, it's convenient to view it as G over K to work with. And then of course we let our matrix algebras B super M just be the linear operators on these finite dimensional Hilbert spaces for the different representations, and we let the action of with the action of by conjugation by the representation just as before, and then we let A be the continuous function on G over K. So this is really the continuous functions on our coadjoint, our fixed coadjoint orbit that works for all of these representations. And for each M, we then have the Dirac operator D sub U super M constructed exactly as we had done before, and we have their corresponding C star metrics L of on each of these algebras, and for A we have its Dirac operator. We can say Levi-Civita, or I could have used anyway. The point is that we have the corresponding C star metric on A, and it doesn't matter which of the three Dirac operators we've used; they all give the same metric. And then our main theorem is that this sequence of matrix algebras with their C star metrics, so these are C star metric spaces, that these converge to the C star metric space A with actually this can be its usual metric from Dirac operator for a quite strong form of quantum Gromov-Hausdorff distance. There are various definitions that have been given, namely the Gromov-Hausdorff propinquity of Latremolleur. That's probably not familiar to most of you. So let me just sketch a little bit how that goes, since I see I have some time to do that. And again, this is complicated, but this will give you some feeling for how this works. So let's let A and B be unital C star algebras, and of course I'll be applying it to the situation where A is functions on the coadjoint orbit and the B is these various B super M's, but just the general definition. So just given the two C star algebras, a bridge from A to B is a quadruple consisting of a unital C star algebra D, and these IA, that's going to be a unital injection of A into D, and similarly for IB. Okay, and then there's a special element in D. This is I still find this sort of magical that this all works, but it really does. Whoops, I'm trying to get rid of this. Yeah, that Latremolleur calls the pivot, and it's a self-adjoint element. It's supposed to be, I mean, what I have here is a little bit more restrictive than his definition, but this is quite adequate for our purposes. It's of norm one, and one is supposed to be in the spectrum of this element. And in what follows, I often won't mention these injections, and I'll just view A and B as being unital subalgebras of D. And for our situation, the bridges that we'll use, the bridge corresponding to the integer M, so bridge from A to B super M, that's very simple. We will let the corresponding unital C-star algebra would just be the tensor product of A with B super M. So that's just the continuous function on our orbit into B super M with the evident inclusions of A and B super M. However, for the pivot, it's not so clear what to use, except that from my investigations earlier, it was fairly clear what to use. Namely, our function is defined by the formula that I have here. So X is an element, and this is going to be a function on G mod K, but define it at first as a function on G, and then see that it drops down. So what we have to look at is that P super M is the rank 1 projection onto the highest weight subspace of H super M. So this is the one-dimensional subspace that's spanned by that Xi sub diamond that I had before. And this function in other contexts is a familiar function. It's what is called a coherent state. And a coherent state really isn't a single state. It's a family of states. And you see these rank 1 projections, they just by using the tracial state, they determine states on the states of B super M. Okay. We aren't viewing them as the states at the moment, but anyway, that's where the name comes from. So this is the pivot we use, which is except for my having worked on these things quite a long time, it's not an obvious thing to do. So going back to the general situation, if A and B are unital C-star algebras, and you have then any choice of C-star metrics on LA and LB can be used to measure any bridge that you are given. Right? And the way Molière does this, he wants to define the length of a bridge, and first he defines the reach of the bridge and then the height of the bridge, and the length is just the sum of, the max of those two. And so what happens, and this is again definitely a long story, is that for these specific bridges that I defined above for our specific setting, I'm able to show that the lengths of these bridges, as measured by the C-star metrics from the Dirac operators that I had defined before on the matrix algebras and for the coadjoint orbits, the length of these bridges converges to 0. And I haven't defined what the propinquity is, but this is quite sufficient to imply that the propinquity, the Gromov-Hausdorff propinquity between our algebra on the coadjoint orbit and these matrix algebras converges to 0. So that's how this all works. And I guess I see I have a few more minutes, so let me go on just a little bit more talking about just so you have some idea of what this general definition of it is all about. So if A and B are unital C-star algebras and you have some bridge, then you have C-star metrics. You first define this real subspace, which you can view as being the unit ball for your semi-norm inside the self-adjoint elements, and you define the same thing for B. And we can view both of these as subsets of D, the C-star algebra D that's part of our bridge. And then the reach of the bridge is simply defined by looking at the ordinary Hausdorff distance between this subspace for A times the pivot on the left, and here you, on the other side, you put the pivot multiplied on the right by the subspace for B, and this is you use just the usual norm of your C-star algebra and Hausdorff distance measured by that, and this one can show this is always going to be actually a finite number. That's not immediately obvious. Okay, and this was how Latremoyer defines the reach of a bridge. Okay? And then to define the height of the bridge, we need to consider the state spaces of A and B, and this is getting closer to the ideas of ordinary Gromov-Hausdorff distance, but even more inside the state space of D, we look at special states, namely the ones that take value 1 on the pivot. This is the level set of D of the pivot, one way of viewing it. And these are the elements on which the states that are definite on the pivot, in the sense that we always have this, or they're the states that are supported on the pivot, if you want. And so we have this special set of states of D that related to the pivot. Okay. And since L super A, since we have a C-star metric, it gives us an ordinary metric on the state space of A, which metrizes the C-star topology, and the same thing on the state space of B. And then what we do is we take these special elements and we restrict those elements to A. And similarly to B, that's when I put in the superscript there. So now these are states on A and states on B. And the definition is that in all of this setting, the height of the bridge is gotten by taking you look at the Hausdorff distance for the metric coming, the metric that A is equipped with, the Hausdorff distance from the restrictions of these special states to the full state space, whereas this is a certain subset of the state space, and you want the Hausdorff distance. And you look at the same thing for B and just take the max of those two numbers, and that's the definition of the reach. And so then then the propinquity, it's the largest metric on isometry classes of C-star algebras that for any bridge you get it's smaller than a bridge, and equivalently, if the length of a finite path of bridges is in the sort of obvious sense between two metric spaces, in other words, you take a bridge from one C-star algebra to another C-star algebra, and then from that one to the next one, and so on, and define the length of those paths to be just the sum of the lengths of the bridges. The propinquity is defined as the infimum of the lengths of these finite paths of bridges. Okay, and then whoops, now I've done everything wrong. I wanted to get the last line here, the last line. So Moyer's main theorem, very non-trivial theorem, is that if the propinquity between two of these C-star metric spaces is 0, then the metric spaces are isometrically isomorphic in a suitable sense of a fairly simple definition of isometric in terms of the semi-norms given the metrics. And I should stop at that point. Thank you.
Well, thank you very much, Mark, for very beautiful talk. So do we have any questions or comments?
Yes, I just have one small question. When you say isomorphic, do you mean that the C-star algebras are isomorphic, or
yes, the C-star algebras are isomorphic. Yes.
Oh, okay.
And
the metrics are the same.
And yeah.
Yeah, and the metrics are the same. Yes. So if I understand correctly, I mean, a bridge is something like like a correspondence between two
yes,
spaces.
that's very much I think sort of the flavor. It's this pivot that I don't quite understand. I mean, that seems to be a new feature, and it's amazing.
Yeah.
It's amazing that it works.
Yeah. It's very nice.
Yeah,
it's nice.
Yeah, that I still consider that to have been very innovative.
Yeah,
putting that pivot in there and using it in this way.
Yeah. And somehow
and
you control.
And that it works. That it works so naturally in my setting. I mean that once you know about coherent states, it's very natural to use that as the pivot, and it just works very nicely.
Yeah, but I mean, it seems that since you have to take like sequences of proximities between two spaces, I mean, so there doesn't seem to be a way to compose these correspondences in a natural manner.
That's right. I agree.
Yeah. Okay.
Okay, so Francesco, you have a question? Please.
Yes, so hi, Marc. So
hi.
I remember this claim about zero propinquity implying isomorphism of C-star algebras, but what I remembered was with dual Gromov-Hausdorff propinquity. So is it the same or a different?
I'm sorry, I didn't hear the end of what you were saying. The same as what? I mean,
if the dual Gromov-Hausdorff propinquity is something different, right? It's not the same.
Yes, the dual propinquity that Latremoulière defined a little bit later. That's not the same. It's a little bit. It is potentially a little bit smaller than the propinquity, but it has even better properties than the propinquity the space of all C-star metric spaces is complete for the dual propinquity is the main advance that gives. But you certainly have the same theorem that if the dual propinquity of two of these C-star metric spaces is zero, then they are isometrically isomorphic.
Yeah, I was a bit confused because it's called the dual, but they are both metrics on the same set, right? Even if they are called, one is called the dual and the other just a propinquity.
That's right. There are metrics on the same set, but one of them is complete. For one of them, the set is complete, but for the propinquity, it's not complete. I don't know that anybody has an actual example showing the lack of completeness. But
there are examples where they are different, right?
Yes.
Okay. So, and maybe, sorry, maybe I ask you also a non-mathematical question, but you changed the terminology a little bit, right? So the compact C-star metric space is the same as compact quantum metric space.
Well, in my very first papers on all of this by compact quantum metric space, I mean, I sort of wanted to say compact non-commutative metric space, but the setting for those was actually order unit spaces. So there really wasn't anything to be non-commutative. And so I just left it as compact quantum metric spaces. And so that was a much more general definition, but it definitely had, when restricted to C-star algebras, it definitely had deficiencies because because a C-star algebra and its opposite algebra with the same semi-norm were of distance 0 from each other, and yet there are examples, of course, where those algebras are not isomorphic as algebras. So you know, the definition of Gromov-Hausdorff distance in this non-commutative setting has had a number of different variations trying to get better and better definitions. But I think I mean, at the moment it appears that Latremoliere's dual propinquity is the best definition for properties. It's not quite as easy to work with. The propinquity, as I described it here, was easier to work with directly. But as I say, that convergence for that implies convergence for the dual propinquity.
Okay, thank you very much.
Thank you. So I guess the next is Christian.
Yes, thank you very much for this talk. I have a question about the last part regarding the orbits and matrix algebras. That construction reminds me a bit like if you have a continuous field or bundle of C-star algebras which are then kind of glued together in a continuous way. So the fiber then above 0 is typically then the commutative one, so the orbit, and then the rest is the other matrices. Is it related to that?
Well, I mean, I'm actually quite familiar with your papers and Klaus's papers on the continuous field structure for these matrix algebras converging to coadjoint orbits. I mean, I have not looked deeply into it, but I have not been able to see a direct relationship there.
Okay.
I mean, one of the things is that for just for ordinary compact metric spaces, Gromov-Hausdorff distance just totally ignores topology. It doesn't work well with topology. I mean, any compact metric space can be approximated arbitrarily well by for ordinary Gromov-Hausdorff distance by a finite subset. So yeah, I don't know what the relationship is between this and your papers, but I may try to look at that, since I think that
I will get a look too. Yeah.
Yeah.
Thank you.
Mm-hmm.
Thank you. So the next is Adam.
Yes, I have a follow-up question. So all these matrix algebras are Morita equivalent to the point, yes? So
Yeah.
in some sense, we are approximating some non-trivial big space by a point, but meant in the non-commutative setting. And my question is the following: do you believe it has something to do with the notion of non-locality in quantum mechanics?
Well, I mean, for one thing, my impression is that physicists view the matrix algebras in several different ways, and that they often view an n by n matrix algebra as being a quantum quantum space consisting of n quantum points and not one point. So I would think that view might have more resonance with locality, but I don't I certainly haven't looked at this carefully. I mean, that would be a major project.
Okay, thank you.
Thank you. So Piotr, please.
Yeah, thank you, Shang. I have a very simple-minded, naive question, if I may, but I can't help wondering whether the K-theory or K-homology, or better still, maybe K-theory is in some sense continuous for propinquity or dual propinquity.
Well, I mean, if you go back, if it were, then if you look at ordinary Gromov-Hausdorff distance between compact metric spaces, it would be continuous there, and it's certainly not.
Okay.
Just because K-theory is a topological matter, and Gromov-Hausdorff distance ignores topology.
Yep. Okay. Thank you.
Okay.
Yeah, it's sad, but
Yes.
well, and I do have a published paper in which I look at the question of, well, if you have two ordinary compact metric spaces like manifolds or something like that, and they're quite close together for Gromov-Hausdorff distance. Well, if you have a vector bundle on one of them, is there a corresponding vector bundle on the other? And that's complicated, and I definitely get some results there, but in a very vague sense, the answer seems to be that, well, the more the bundles twist, the closer the spaces have to be to each other in order to have bundles on their nearby spaces. Just to put it very vaguely.
Yeah.
So even in that setting, really, K-theory doesn't work terribly well.
Yeah.
I mean, one could say something, but it's not ideal from that point. Well, and I also have another later paper in which I prove I give a similar idea for projective modules over CSAR metric spaces. So again, in that setting, you have the same thing that if two of these compact C-star metric spaces are close enough together, and if you have bundles on them that are close, that don't twist too rapidly, then, well, it's the same idea as I said before, but does extend to the non-commutative setting.
Yeah, the projective modules and vector bundles. Yes.
Yeah.
Yeah, thank you so much. Do we have any questions or comments? So if not, let's thank Marc again for fabulous talk.
Well, very good to see you all.